Hello, everybody. I'm Mohammad Khajanejad from Arizona State University, and I'm going to talk about my joint work with Theo and Jean and my advisor, Dr. Yang, on interval observers for state and model estimation of partially known nonlinear systems. So as you know, cyber physical systems are safety critical, and in such systems, state estimation is important for fault detection, urban transformation, etc. Also, in many practical applications, dynamic models are often only partially known. So a motivating question would be, can we develop algorithms that combine model learning and model-based set membership estimation approaches in such complicated settings? So there have been several work on model-based interval observers when the dynamics of the systems are known for different classes of dynamic systems. Also, set value data-driven approaches when unknown dynamics are unknown uh, have been developed in many works with the objective of using input-output data to find a set of dynamics that frame the unknown system dynamics for example, univariate Lipschitz systems, multivariate Lipschitz systems, and Holder systems. However, to best of our knowledge, interval observers for such data-driven models have not been considered in the literature, which would be the subject of our work. So we consider partially unknown nonlinear discrete time systems with these dynamics, where X is continuous state, D is unknown dynamic input, W and V are process and measurement bounded disturbances, U is the known input signal, F and G are known functions, and F is assumed to be mixed monotone, which we will talk about it later. H which describes the dynamics of the unknown input, is an unknown function. However, it is assumed to be Lipschitz continuous in each dimension, and its Lipschitz constant is known without loss of generality. Otherwise, we can estimate it using our previous work here. So given such a system, we're interested to design a stable observer that simultaneously finds uniformly bounded intervals of compatible augmented states. By augmented states, I mean the augmentation of state and unknown input. And our observer learns an unknown dynamics model for the unknown function h. So in other words, we want to find upper and lower framers such that it is guaranteed that the actual value of the state is within the lower and upper framer. And also we want to learn a data-driven model approximation h upper bar and h lower bar such that function h is within these upper and lower abstraction models. So we used some preliminary tools in this work. First of them is a fine abstraction, which had been developed in our group. So we showed that by solving a linear program, given a nonlinear function f, we can find upper and lower fine functions such that f of x for any x in the domain of f is within the value of these upper and lower affine functions on X. Next, we used a mixed monotonicity and decomposition function. So a function is called mixed monotone if it admits a decomposition functions fd, which is a function from the higher dimensional space of x times x. And fd satisfies three conditions. Fd of x and x coincides with f of x. Fd is monotonically increasing in its first and monotonically decreasing in its second argument. So if such an fd can be found for f, then for any x within x underbar and x upper bar, fx is bounded within fd of x upper bar and x underbar and x upper bar, and fd of x underbar, upper bar, and x underbar. So given these tools, we designed our observer, which consists of three steps. The first step is state propagation, where we propagate state framers through decomposition functions and fine abstraction. The second step is the measurement update step, where we want to refine or intersect the propagated set with the inverse of the given observation sets through the nonlinear observation function G. So this process is called a set inversion process, which is a hard task for a general nonlinear function G. So we to tackle this difficulty, we approximate this set by means of a fine abstraction, and we do it through an iterative process. So to give you some sketch, starting from an initial interval, this, for example, green interval, we instead of computing the inverse of y through the nonlinear function g, we compute the inverse of y through the affine abstractions of g in this initial interval, and this gives us this red interval. And then if we repeat this process iteratively and redo everything in this new interval, then we get a sequence of the framers, upper and lower framers. These sequence of framers are shown to be convergent, and they converge to final upper and lower updated framer for the states. So this summarizes our iterative measurement update. And then finally, given all the data, input and output data for the nonlinear function h in a time horizon t, we leveraged our previously developed method here to compute lower and upper abstraction model or approximation functions for H through this process. And this is called model learning and is the third step of the observer. So our observer, our design observer satisfies several interesting properties. The first one is the correctness, and by that we mean that the actual value of the state is within the computed lower and upper framers. Also, we showed that our input model estimation becomes more precise or tighter over time. Also, we showed that if some sufficient condition holds, then our observer is stable, and by stable, we precisely mean that the interval width sequences are uniformly bounded. These stability conditions are in form of feasibility condition, and the good point is that the feasible set is a countable and finite set, so the feasibility condition or the stability condition can be checked easily by enumerating all possible cases. Moreover, we showed that if this stability condition holds with strict inequality, then we can compute upper sequences for the interval width sequences. And this computation is done through solving an integer program. And again, the feasible set for this integer program is a finite set, so it can be done by enumeration pretty easily. So after designing our observer, we applied it on a discretized predicate prey system with 2 states and 3 outputs. We showed that the stability condition holds with strict inequality, so we expected uniformly bounded errors and convergent upper bounds. And the simulation results actually shows that the actual value of the state and unknown inputs are within the computed lower and upper framers, both for states and unknown inputs. And also as for the errors, we see that the actual estimation errors are within the interval estimate width, and they are both within the computed upper sequences, these green sequences, which are uniformly bounded and convergent sequences. And this figure shows that the actual unknown input function is within the computed upper and lower abstraction models. So with this, I'm going to conclude that we combined a model-based interval observer approach and a data-driven learning method. We proposed interval-valued state and model observer for partially unknown nonlinear system. We provided sufficient conditions for correctness of the observer. We proved that the learned input model becomes more accurate over time. We derived sufficient conditions for stability of the observer, and we found closed form expressions for error upper bounds and conditions for their convergence. So in future, we're interested in designing tighter decomposition functions, in providing necessary conditions for stability, and in applying our method on more general uncertainty sets, such as constrained zonotopes and zonotopes bundles. Here is a list of the references that have been used in this work, and by this, I'm going to thank you all, and I'll be happy to take your questions.